Okay, today we are talking about two new parent functions, x to the third and 1 over x. And hopefully you'll learn how to transform them, as in move them around and stretch them and all that stuff. And then write equations for ones that are already transformed. Like we give you a stretched 1 over x function, and you have to figure out what was the equation for that. All right, one thing at a time. Here's the new function. Everybody graph these points really nicely for me. Of course, what I'm really doing here is making an XY chart. And I am saying that this, if I plug in a 1, I end up with 1 to the third, which is 1. 1, 1 is on my graph. Who can name another point that would be on my graph? If I stick in a what, you get a what? Yes, sir. 2 goes with 8. You are correct, sir, because I put a 2 there, and 2 to the third is 8. So 2, 8 over 2, up 8. 1, 2, 4, 5, 6, 7, 8 right there. And now let's throw in some negatives. Negative 1. If I put in negative 1, what do you get? Nope, it's negative 1. Oh, wait. It is negative 1. Sorry, my bad. When you put in a negative 1, I was thinking it was going to have, like, this power was going to make it turn into positive 1. But negative 1 times negative 1 times negative 1 is negative 1. Negative 1, negative 1. So it's down here. Can you see where this thing is going to go? So if I put in negative 2, I would get negative 2 goes in there. Negative 2 times negative 2 times negative 2 is negative 8. And so it's negative 2, negative 8 is down there. And try to catch the flow of this thing. It goes like that. And this spot right here is special. It's called an inflection point. At that moment, the graph stops. It's rising the whole time. You remember this? Increasing at a increasing or increasing at a decreasing. You remember that stuff from like a month ago? Okay. Well, it's increasing the whole time, right? But it changes from increasing at a decreasing, because, you know, it's slowing down. Right at that exact moment, it changes from increasing at a decreasing to increasing at an increasing. So it starts going faster and faster, because remember, steeper is faster, right? And here it's not very steep, but when you get to here, it's very steep. Okay, so it's called an inflection point. It's not a big deal. I'm just trying to let you know. You'll learn more about that next year in pre-calc. Okay, so that is your new function. So let's say that we wanted to move it to the right. It isn't too hard. You just think, all right, y equals x to the third. Move it to the right means like minus 2. How far did I just move it? 2 to the right. So then I would take every dot on it and move it 2 to the right. And the whole function will move 2 spots right, like that. 2 spots over, 2 spots over, 2 spots over, 2 spots over. Okay, now there is an example of one, oopsie, that has been transformed. I can't get that little point behind there to move, but anyway, I'll have to try to ignore it. Okay, so let's say I gave you one that was already transformed, and it was here. Imagine for a moment this was my function. And I just gave you that function. And I said, what's the equation for it? Could you write me the equation for that? We'd start by saying, well, I can tell that that's one of those kind that makes the snake kind of a shape, where it's kind of like slithering away, okay? Anything like that must be an x to the third. So I would write y equals x to the third. And then I'd think, okay, but it's been moved. Which way was it moved? To the left. How far to the left? 6 spots to the left. So then I can go inside here. I'd have to say x minus 6, and I'd cry a little bit and mark it wrong, because y? It should be plus 6, because it's to the left 6. So there we go. Okay. So that would be an equation that you'd have to write. Or let's say even more challenging, I make it like this red one here. And I go like that. And I say, what's the equation of the red one? And it's close to the equation of the blue one, but it's not the same thing. It's been flipped. Up, down, flip. Here, I'll put it back in. It was there, the blue one. Now do you get if I flip it up, down? This part goes down there and this part goes up there. I get the red one. So if that's an up-down flip, otherwise known as a what? Is that horizontal or vertically flipping? Vertical. It's a vertical flip. I need to throw in a negative. Where? Yep. Vertical's on the outside, right? So there would be your equation. That's as complicated as it gets. Yes? This one is weird because when you flip it horizontally, you also get the same thing. And I want you to think about why that is. If I have y equals x to the third, and I decide to put a negative on it, do you get that it wouldn't matter if the negative was on the inside or the outside? Because the power is to the third power, and so it doesn't care if you put the negative inside or outside, it's going to do the same thing. So it actually makes sense that when you flip it left, right, or flip it up, down, it'll get the same result. Because let's say I put a number in like 2. If I make it negative like this, or if I make it negative like this, it's going to be the same thing. Either way, it's negative 8. That's why putting a negative on the inside or the outside, in this case, does the exact same thing. It's a weird thing about these graphs, and that's a good catch. Yes? Maybe it'll help you if I move them to the right. So if I start over here, and I start over here, now if you flip the blue one up, down, or left, right, do you see how it lands right on the red one? Yep, either way. So horizontal and vertical flips are identical when it comes to x to the third. Okay, that's a little bit of a mind bender. Now let's go to, oh wait, this one. So many kids on the test got this wrong. Is that negative on the inside or is that negative on the outside? Outside. That is on the outside. If I meant for it to be on the inside, I would have had to put it in parentheses. Now it's on the inside. Now remember though, does it matter in this case? No, on this kind of problem it doesn't. But on the test we had before, that was x squared. And then it did matter. And it was like, should I flip the parabola up, down, or left, right? Because that's totally different. And it does matter. So that's on the outside. Now it would be on the inside. All right. So moving on to this one, 1 over x. It's the other parent function that's brand new. You've never seen one like this before. And it introduces something called an asymptote. It is a dotted line that the function gets infinitely close to but will never touch. So a strange concept to be infinitely close to something but never actually touching it. Like I get this close to touching your water bottle. I get so close. I get infinitely close. And it's just like painful. It's like so close, but it's not quite there. And it has to get closer and closer and not touch. Okay? Seems like eventually you'd have to touch it. Nope. The best example I can give you on this of getting infinitely close to something but never getting there is, let's say you had a swimming pool full of perfectly pure water. And then you put in just a little bit of poison. Okay? Now your water isn't perfectly pure anymore, is it? Let's say we take a whole bunch out, like we dunk like buckets in there, and we throw a bunch of the water out. And we put in more pure water. Is it perfectly pure now? No. Can you ever get it perfectly pure again? No, you can't. Not unless you actually filter it all. And if you take all the water out, that'd be different. Okay, but if we just take some of the water out and dump it and pour in pure water, it's going to get purer and purer. Now, realistically, there's a lot of toxins where if it's only a tiny bit, it's not going to hurt you. You know, there's a lot of things like that. Like in our water at home, you drink water out of the tap, there's a teeny tiny bit of lead in there. Okay, you can't get it all the way out. But if you have too much in the water, it can really poison you quickly. But if there's only a teeny tiny bit, your body can handle it. It can filter out poisons like that. The air you're breathing right now is recycled. It used to be in a dinosaur fart one day. But it's been recycled, and it's been kind of it's still got little tiny particles. In fact, they've done the research on this, and like every person's breath that they have exhaled in the course of time has let out particles into the air, right? You're exhaling air particles, okay? I'm being very non-scientific here, but the point is there's a little tiny bit of the exhale of every other person that's ever lived. Now, it has to be long enough, though, because some baby that was just born like today in China, I can't be breathing its exhales yet, right? But just there's so many particles in each breath that you take in that you're actually breathing in exhales from people from around the world over time. Okay, it's kind of a weird thought, isn't it? Yes? It's always going to be what? It'll never touch that line. Even if you continue forever this way, it's never going to touch it. It's going to get closer and closer and closer, but never touch. That's more of a concept. It's kind of like a concept like infinity. You can hurt your brain thinking about it for too long. You just trust that it's going to get closer and closer, but never touch that. Okay, so then if I want to move this whole function to the right, it's not that complicated. If I go like -3, there, I just moved the function to the right, 3. As opposed to if I put it -3 out here, which way did I just move the function now? Down 3, yes. Okay, so if this was your function, it would take the parent one, which was on the board, and it would move it 7 to the, what's this mean? 7 to the left, and then down 5. Good. And you start on the inside first, right? So you go 7 to the left, and then down 5. So here's 7 to the left. 1, 2, 3, 4, 5, 6, 7 to the left. I left a dot behind. And then I'd move the whole thing down 5. 1, 2, 3, 4, 5. There's my new function. And notice those asymptote lines should really move with it. I'll leave them there just because they're a pain to move. But there, now it's got its new asymptote lines. Okay. Now we aren't going to do much with stretching this kind because it's almost impossible to tell if you stretch it. So don't worry about stretches when it comes to the 1/x function. The other one you can kind of tell, even it's kind of hard to do stretches on, but this we will not mess with stretching. Yes? Are there what? The domain and range on this is a little unusual, so we should talk about that real quick. So I'm going to get it back where it was in the first place. Okay? And the domain and range on this is, domain is from left to right. So you'd think it's from negative infinity to positive infinity. But along the way, as you're moving from negative infinity to positive infinity, there's something that stops working. It stops working at 0. See, as you're going from this to this, you don't get to completely drive across that dotted line. So its domain is like this. So you'd say from negative infinity to 0, and then it starts again at 0 and goes to infinity. This is written as a number line. I think it's easier to understand. But this one's written in interval notation. Range is the same way on this. The range on this is from low to high, and it has to get up close to this line, but it never actually touches that line. So it's from negative infinity until it hits 0. It doesn't touch 0. And then it starts again at 0 and goes to infinity. So the range is identical. Yep, the domain is from left to right, correct? But there's something you can't do as you go from left to right. You never can touch this dotted line. So it's everything except 0. The domain is everything works, except it can't be 0 because, see, when it gets here, it can't be that. And then it starts up again on the other side, and it can go forever.
Oh, so it just doesn't hit 0.
Yep. Yep. So it's like this, with a number line with only 0 with it, it can't be. So that's your domain.
So it can be like negative 0.1.
Yep. It can be anything except 0. All right. So now your homework for today is, of course, about this. I feel like we had some really good chance to talk about top 20 stuff, but that means today you don't have enough time to get a full assignment in. I'm going to just ask you to do the evens and the even letters. Okay, so if there's A, B, C, D, E, F, G, do the even letters. I know that's weird, but that would be like the B, D, E, F problems. Evens and even letters. All right. Okay, good clarifying question. There's 2 worksheets. One of them is called investigation. The way this lesson was supposed to go, or could have gone, was I would say, here's a calculator, figure out what the things look like. And you would have investigated and figured out that, oh, the x cubed looks like this. You do not need to do the investigation for tonight. That was going to be done in class, so just skip the investigation thing. Do the actual homework worksheet, just evens. Have a great day. Yep, take care.